Welcome to the channel. So in this video we will continue the quantum chemistry. So in this video we will start from the de Broglie relationship. So what the de Broglie suggests that every moving matter, every moving matter, every moving matter have dual nature. It means it have both particle as well as wave nature. And he suggests a relationship between wavelength, which is lambda wavelength of the wave associated with that moving particle, which is lambda is equals to h upon p. Here p is the momentum of particle, which is equals to mass into velocity. So h upon v, here h is a Planck's constant. H is Planck's constant. So the value of h is relatively very less. H is equals to 6.626 into 10 to the power minus 34 joule second. So the value of h is very less, like this is 10 to the power minus 34. So the value of this lambda is relatively very less here. But if we increases mass, on increasing mass of matter, then we can see that lambda is inversely proportional to mass, right? Because momentum is mass into velocity. So on increasing mass, the lambda basically decreases. So in macroscopic world, in macroscopic world, like in which we live, it consists of humans, animals, trees, etc. So it have really a big mass, and they have relatively very less value of lambda, very less basically wavelength. So it basically a negligible thing. But in reality, according to the relationship, every matter have a wavelength. But in the macroscopic world, the wavelength is very less. But in the microscopic world, like where we talk about the atoms, electrons, mass is relatively very less. So we cannot neglect the wavelength. That wavelength have something which can trigger us. So we have another relationship or another main thing which we can talk about, which is Heisenberg uncertainty principle. So what is Heisenberg uncertainty principle? Heisenberg uncertainty principle basically states that we cannot we cannot calculate accurately uh, momentum and position simultaneously. We cannot calculate. There will be uncertainty in position as well as in momentum. So the uncertainty in position is represented by like this delta x. This is uncertainty in position, and uncertainty in momentum is written like this: uncertainty in momentum. So what is the uncertainty? I just give you an idea. Okay, let's suppose for a particle, if we could able to calculate wavelength accurately, let we able to calculate lambda wavelength accurately. How we can calculate the lambda accurately? See, if we knows the mass and velocity, so by using this uh, equation, we can calculate the lambda. So on calculating lambda, let's suppose we have a wave which is like this. Okay, which is like this wave. This is from, let's suppose, minus infinity to infinity. If we could calculate the lambda, which is wavelength, the length between these two crust, or the length between these two continuous trough and crust. So if we could able to calculate this lambda wavelength, then it means in the whole scenario from minus infinity to infinity, this same lambda will going to repeat. So our particle probability of finding particle is maximum where the amplitude is maximum, right? So this value, this height will be the amplitude or displacement. So according to this particular example, where we can find the electron, where is the probability to find electron or particle is maximum, is this point, because here the amplitude is maximum, and similarly here also these all have the same probability. So we can find the particle at any of these points, but at a particular time the particle is at a particular point, right, at a particular position. So here we are very uncertain where we can find the particle, because it is very uncertain. At any time the particle should be at a particular position, but according to this particular example, we can find particle anywhere. It can be anywhere in the region, because at this point also, these are the points where the probability of finding particle is maximum. So this is the example which suggests us what is uncertainty. We can find the particle at any of this point, but we have a problem that at a particular time the particle is at any of the one point. So this is called uncertainty. So that's why we cannot find a position of particle if we knows the lambda, or if we knows the momentum of particle. And hence de Broglie suggests this equation, which is uncertainty in position into uncertainty in momentum should be greater than equals to h upon 4 pi. So this is the equation from which we could able to relate what is going on. So let's suppose this uncertainty in position would be greater than equals to h upon 4 pi into uncertainty in momentum. Let we could able to find the momentum precisely, that we could able to find, then this uncertainty in momentum would be zero, right? So in such case, that this value uncertainty in position would be like this is a constant, and in the denominator it is zero, so it would be infinity. It means we could not able to find the position precisely because it reaches to the infinity level uncertainty. The error would be maximum. And similarly, if we could able to find the position precisely, and simultaneously we could not able to find the momentum precisely. So this is the uncertainty principle. After this, we will going to talk about the standing waves. Standing waves. The two main thing which we should know about standing waves is they have definite frequency, and they have a particular shape, or with time their shape do not change. Here shape, or we can say amplitude. For example, how standing wave could look like. Let's suppose we have a string between these two pillars, and from one pillar, if we start putting some vibration in the string, then it could look like this. Let's suppose it will form a wave like this, right? This whole string would go up, and again a possibility that this whole string would go down like this. Wait, like this. So this will go up and down like this. So this is an example of standing waves, because on an average the shape would be same, or we can say symmetric, we with a particular amplitude which do not change with time. Similarly, another type of wave which can be formed is like this. One case is like this. Another case could be this will go down. So if we see that at a particular point, this point would not move at all. This is a fixed point. Like if you could able to feel its amplitude even do not change, even whole amplitude on an average do not change, but this thing, this particular point do not get displaced. So this is called as node, or node is a point where the probability of finding anything is zero. We will talk about it in future. And another possibility here is that we can have this type of wave. Okay, let me shift this to here. Okay, or it could look like this. Just assume it's metric and both are same, because it cannot become so perfect here. Again, here we can have 2 points which can act as node. These are 2 points which can act as node. It will not change. Again, this is a node where there is no displacement basically. So basically this particular shape or wave have no node. Here node is equals to 0. In such kind of wave, node is equals to 1. In this wave, node would be 2, and so on. It means how many standing waves we can have. So we can have infinite standing wave. Fine. So let's suppose, for an example, we have a particular particle in a box. Particle in a box which is moving. Okay, so let's suppose this is a completely closed box. See, and here we have a particle. What particle will do, it will just, suppose it will strike to this wall and get deflected here and goes here. So this particle would consist of many waves, right? And in so many waves there can be many standing waves possibility. There can be a possibility of many standing waves. So let's suppose this particle has this kind of wave, right? And when it deflected, it can have such kind of wave. So it can have standing wave. So these are the waves. Let's suppose this is a atom, or you can assume it as electron, which is a confined in a particular box. This box can be a atom, right, or nucleus. Why I'm saying this? Because if you could assume that this is nucleus and this is whole atom, the periphery of the atom, electron could not able to go from this particular surface easily if we do not give them energy. So we can assume like this particular electron is confined within this system. So this electron can have many standing waves, and that standing waves called as atomic orbital, and such standing waves called as orbital. For example, s orbital, p orbital, d orbital, and so on. These all come when electron is confined in the influence of proton. Okay, so for this video, this is enough. In next video, we will talk about postulates of quantum chemistry, and what is action, what is the time dependent Schrodinger equation, and so on. Thank you for watching the video.